Physics 2, Lab 6. Experimental setup. The materials used were a bar magnet, aluminum foil tube, smartphone camera, and a measuring stick. And we use that to get all the measurements as you see here on the right for the tube, its length, radius, thickness, and then also the magnetic moment. There are three key physics concepts that we have to know to do this lab. Faraday's law, which states that EMF is equal to the magnetic flux over time, and then you negate that. And so then changing magnetic flux through aluminum rings induces an EMF. That's the reasoning behind what we have to know it. And then induced EMF drives current through resistive aluminum rings. Each ring has a resistance of R. And so you have to know Ohm's law, which is EMF is equal to I times R, I being current, R being resistance, and current is equal to EMF divided by resistance. And then the current carrying rings create magnetic fields. And specifically, these magnetic fields have a force. And so the magnetic force on a dipole is equal to the gradient of mu dot B, B being the magnetic field. And by Newton's third law, magnets experience upward force. This force opposes the motion, Lenz's law. And then results. For trial 1, we had 1.82 seconds. Trial 2 was 1.79 seconds. Trial 3 was 1.85 seconds. Then we had 1.81 seconds and then 1.83 seconds. And on average, this was 1.82 seconds. And then for the computational model, for the components, we had to create a magnet component, tube component, and then we also had to account for some dynamics as well. This was the dipole field formula that we used. And we also we used the initial position as above the tube. And then we modeled the tube as a stack of 50 non-iterating conducting rings, each with radius capital R and thickness delta Z. And then for the dynamics, as you can see here, we had to calculate the magnetic field at each ring position, and then also calculate the magnetic flux over time for each ring as the magnet moves, and use Faraday's law to find the induced current in each ring. And then using that to calculate the force on the magnets from all rings, and then update that for the position and velocity using FNet. Here is a picture of the model visualization, and then here's the code on the right as well. So we had to make a couple assumptions for this lab. Point dipole approximation, rings don't interact, the tube is stationary, there's no air resistance, uniform current distribution, quasi-static approximation, which basically just means that induced currents respond instantaneously, and then aluminum foil properties are constant, which just means the temperature effects are negligible. And then why the model might differ from the experiment. If the simulation time is shorter, the magnet falls faster in the model. So point dipole approximation breaks down close to the magnet, air resistance isn't included, and the tube might have vibrated in the experiment. If the simulation time is longer, then the magnetic moment value might be overestimated. Aluminum resistivity might differ from the standard value, and then there might be an error in the foil thickness measurement. Improvements could be that we could have more accurate magnetic moment measurement, account for finite magnet size, include temperature-dependent resistivity, and then model current distribution more accurately. What if the resistivity of the conductor were reduced as close as possible to zero? After doing some of the math, the result would be that the magnet would fall even more slowly, and it could potentially levitate if forces equals the weight. And in a superconductor, this would be known as perfect diamagnetism, also known as the Mesmer effect. What if holes or slots were cut into the tubes? Well, think of some of the consequences. Smaller induced currents, weaker magnetic force on the magnet falls faster, closer to a free fall. Then the effect on the ring currents would be that the slots break the continuous conducting path, and ring currents cannot form complete loops, and current must flow around the holes. So effectively, it increases resistance dramatically. Conclusion: electromagnetic induction successfully demonstrated through the magnetic behavior in this experiment. And point dipole approximation provides reasonable accuracy. And just for laughs and giggles, me and my team, we came to an agreement that the computational model agrees with the experiment about 3.4%. And Lenz's law correctly predicts opposing force direction. Thank you.